this is I'll talk in a little random way. And I would like to mention some puzzles. And those puzzles usually I have in my teaching and research. They are interesting. Yeah, it is. For me, they are very interesting. And most of them I have no answer. So I have some ideas. That's what I want to talk. So the first thing I would like to mention, not about fundamental unit, but let's think about what is a fundamental unit. Usually when we study in junior high school, we know the unit is like a length, time, and mass. And later, we know we don't use time as a fundamental unit. We use time as a right unit. We're using speed of light. And then, this should be the speed of light. Natural unit. And in science and physics, people like to use natural unit, which is right, because it's difficult to say, well, what is the most fundamental mass, length. If we are talking about meter or meter, it's actually related to the size of the earth, that is not very much. And so in high energy physics, people like to talk about CGH and then using that to write the length. Okay? And so for using CGH, we have we call the ground length, like GH/CQ. And ground length usually considered the smallest length. So we usually think the Big Bang or the universe is like the size of ground length. That's how we take it. And okay, usually you can see that is the smallest length. But the problem I have here is that can length be a fundamental unit? Well, let's think that if length is some kind of fundamental length unit, is the smallest length unit we have, then some unit or some length should be multiple of the fundamental unit. But we know that we have the Pythagorean theorem, right? So we have s squared, b squared equals c squared, and that you have learned in junior high. Okay. And now let's assume we have a equal ground length, b equal ground length, then we have c, the hypotenuse equal square root 2 of L. How we know the square root 2 is not the multiple of 1 or 2, it's 1.4. That means you have something that's 0.4 from length. That's not strange. So that means we cannot have length as a fundamental unit in more than 2 dimensions, more than 1 dimension. In 1 dimension, yes, we have 1 ground length, 2 ground lengths, 3 ground lengths. But if we have 2 dimensions or 3 dimensions, we cannot have that. So that means length is not very fundamental. And usually we think it's fundamental sense. But what is more fundamental? I would say length square is more fundamental, right? Why? Because if even using the Pythagorean theorem, we can have 1 square, b square, and then c will be 2 square. So if we think about length square, it could be some fundamental. So we won't have that problem I just mentioned. So which means length square in some sense is more fundamental than length, right? So now the question, do we have any fundamental physical quantity in units of length square? Well, the easiest thing would be the inverse of cosmological constant, right? We know cosmological, that's the value that we have. Cosmological constant about 1.1 times 10 to the minus 56, and the inverse, the inverse will be a very, very big number. Actually, the inverse is related to the size of the universe if the universe is static, right? So that's why Einstein first can assume the static universe, and then he cannot find a solution for a static universe, so he assumed there's a cosmological constant, that's the original cosmological constant. And then the cosmological constant is related to the size of the universe. And so that's lambda is equal 1 over s squared. And so if lambda is some kind of fundamental unit, so that means the universe, the size of the universe, or the s squared, is some kind of fundamental quantity. But it's very large, it's still very small. Even in some kind of, I would say, fundamental magnitude constant in the universe. But that's not right? It's not right. Why? Because our universe is expanding, right? It's not static. So maybe you think it's not quite right to say that way. But when you think about that, what is the cosmological constant? Is it some kind of physical quantity? People think about it more like dark energy. Or actually we can consider lambda as some kind of geometrical property. So for those students who took my course about cosmology, we should have learned this. We're using actual principle to derive Einstein equation, right? We can, of course, we have tensor curve, energy stress tensor curve that I did not write down here. When you do the variation, you consider this action, and you do the variation to this, then you derive Einstein tensor. You can derive Einstein tensor by using the action. But now, if you want to derive the Einstein equation with cosmological constant lambda, how can we do it? We do the variation for this one. We consider lambda is some kind of constant, and the R is a Ricci curvature scalar or some kind of Riemann curvature scalar. So we're just using this, then we can derive Einstein equation with cosmological constant. So then, what's the meaning of the two lambda? We're using this, and then we can derive the Einstein equation with cosmological constant. So we know R is the curvature of our universe. But then, what is lambda? You can say, well, it just is a quantity, right? But actually, if you think about some kind of manifold, it's more than, for example, you have the m cross n manifold, right? Then the sum of the scalar curvature of m and the m will become the curvature of m cross n manifold. So that means so that's what I mean. What I mean is we can consider two lambda as a curvature of the two spheres, but it's not the dimension of the main universe. It's some kind of extra dimension. And it has a radius a, and lambda will be equal 1 over a squared. And so our universe actually has a curvature of r plus 2 lambda. And that means our universe may have actual dimension of the two spheres with a radius square root 1 over lambda. It is too difficult to imagine. Actually, it's very difficult to imagine what is the actual dimension of two spheres. But let's simplify. Let's simplify that. We simplify that. We consider the envelope of the geometry. We consider the envelope in 2 dimensions. Now, we consider cylindrical. For example, we have some fixed cylindrical. We have fixed circle here. So we have circle here, and then we have 1 dimension in the cylinder. We have expanding in this dimension. Okay, so that's a very So my idea would be, okay, we gotta fix two sphere, not one circle, it's two sphere, and then our universe is expanding in this way. And that would naturally very easy to describe what is the cosmological constant. So that's a purely from your nature. The question is, how can we prove it? I don't know. So that's leave to you. But that's a very simple idea that we can express. And to me, it's very nice way to express cosmological concept. Using geometry, just mean we have an additional two field dimension, another dimension. Okay? I mean, we are embedded in a very big universe. Usually, we just living in this surface, so we only feeling limits in this direction. We don't feel this curvature, and this curvature become the cosmological constant. That is remarkable.
I'm sorry, what is a blue sphere?
Blue sphere is like a sphere, like two dimension. Yeah, that's usually if we have three dimensions, so the surface is two sphere, two dimensions. The surface is two dimensions. Okay. I hope this is too easy for you. Because there's some difficult physics math here. Okay, now. Yeah.
I like this length square.
Okay.
But at the beginning, you mentioned about the Pythagorean. Well, why does it have to be
As a Pythagorean?
Pythagorean?
Mm-hmm. I mean, for example, if we can say that LP is the smallest length,
Right.
then any length should be multiple
I
of
understand
this,
that,
right?
right.
But now, if we are in a two dimension, then we can have Pythagorean here, right? So then the length.
Yes, but it could be the in three dimension.
Three dimension, you still have that problem. You
Right.
square root, so it cannot be multiple of that. But it can be multiple of length squared. It cannot be multiple of length. But it doesn't matter how many dimensions, right? It's more than one dimension. So you have this problem, right? But if we length square, then no problem, right? It's just a square, b square, c square. B square, right? But it must be multiple of length square. So you can have you can consider length square or the square function. Okay? Yeah, I think I mentioned some of this in my pitch, right? Yeah.
They don't remember.
Okay, but then I did not mention about how we can expanding and with this another two sphere. Okay, that's bad. Okay, now let me talk about another problem or suggestion puzzle people have. Everyone knows we have supermass black holes, and we also know we have stellar mass black hole. There's a very issue that usually people say, why we don't have intermediate mass black? A lot of people try to look into that. And the existence of that is argument or debate. But in any case, I mean, if even we have intermediate mass black hole, they are very big. And it's very difficult to discount. So, why we don't have intermediate mass black hole? Well, the first thing is, well, probably the mechanism to create black hole prohibited, and we cannot create that. But that's not quite right, because we already know there are many mechanisms that can create intermediate mass black hole. It is theoretically. For example, we have a cold collapse star cluster. If we have clusters where they evaporate, then some of the stars fall into the center, some of the stars will go away, run away, then because of energy conservation. So the central will become cold collapse, and then we should have, if like 10 to the 5th or 10 to the 6th, we should result in like a central black hole, like K to the 3 or something. but we should have some intermediate mass black hole. There are many different methods that we can have intermediate mass black hole. But the problem is we cannot see it. So where are they? Where are the intermediate black hole? Intermediate mass black hole? Or why is it difficult to find them? Well, my answer is quite simple. That's a much simpler than people expect. This is easy because we are dynamical fish. What do I mean by dynamical fish? My answer is if we have any intermediate mass, most of intermediate mass black hole should have fallen into the central mass black hole if they are within the galaxy. Okay? Because of dynamical friction. If you are more massive, then you have more dynamical friction. You have very massive star, black hole surrounding by a star, right? Then you can lose your energy when you collide with a star. Okay? That's kind of dynamical friction. I think I also talk about this in my lecture, and people study galactic astronomy. Okay, most of them forget that. And so we should have that dynamical correction. So if you look at the solar neighborhood, well, this is time scale. You can imagine it's very similar to relaxation time scale. And a solar neighborhood, well, according to my note in galactic astronomy, a solar neighborhood, the time scale will start to relax, which means that change all its energy, or lose all its energy, or they obtain the similar energy of the region. Then it's about 5 times 10 to 13 years. So that's why we argue that in a star, in a galaxy, like our sun neighborhood, our sun are not relaxed yet, because it takes much longer than the age of the universe. But what happens if we got the intermediate mass black hole? What is the time scale? The time scale for the intermediate black hole to lose all this dynamical energy is only like 5 times 10 to 7. That's in the solar neighborhood. If you are in the March, Central, or something, it should be even shorter because of the density of stars. And if you have much higher mass, the time scale will be much shorter. So that's why you cannot see intermediate mass black hole. It's very difficult to see the intermediate mass black hole because it cannot survive very long in our galaxy. Well, I did not do this in particular. Yeah. Any question? Yes.
It takes only 10 or 7 years from solar neighborhood to maybe get
Galaxy
the center.
Yes.
What about when its path was there? Can it collide more and get more massive?
No, when I say collide, it is a dynamic friction. So which means you don't really collide with each other. They just have an influence together. When you pass, for example, a star pass by, then the star get energy. The intermediate black hole loses energy, and then you keep falling into the center of the galaxy.
Is it possible for the tidal destruction or neighboring stars or someone that comes in the gravitational field to be affected?
But I think that, again, that is very small, very similar to the changes of stars. Even it's slightly larger, because the gravity is still very small. But the dynamic friction, because the long range force, so we can still dynamic friction, and we can lose energy very quickly. Okay?
I'm sorry, I also don't understand this. What happened if an intermediate black hole just formed at the center of the globular cluster? It just stays there, right? Just like any other star. So why does it have to fall into the central star?
Oh, I'm talking about, although I'm using the globular cluster, for collapse example, right? So what I say is if you got an intermediate mass black hole in galaxy, then you fall into a certain okay. On the other hand, if you have intermediate mass black hole is formed in early cluster, but is far away from galactic plane, in that sense, then the number density will be small, so the relaxation time will be long, so it probably is still big, okay? But the point is, if you are not in a very dense, not actually very dense, if you are in a very, the density is very, very low, right? Then you probably don't have any information. What I'm talking about here is if you have some intermediate mass black hole in the wrong galaxy, then you go into the central very quickly.
No, I still don't understand. There's no friction.
It's a dynamic friction.
What was that?
That means, well, we have a very massive star here, and a less massive star. So when they are close to each other by the gravity, even the mass one lose energy, the small one will gain energy. And that's a problem. So that doesn't have to be interact, doesn't have to collide or doesn't have to be.
It's just 10%. Has we detected ever the trajectory or something, the evidence of?
So I say, if we have something that, for example, we have form at the beginning of the dark, right? But there are some mechanisms like you have intermediate mass black hole formed from the collapse of American function. Then those intermediate mass black holes will already fall into.
But the indirect evidence of dynamical friction, some low mass being more high speed than the.
It might still possible to find something like a 100 because the time scale is small. But for like a 10,000 or 100,000, it will be very good. But it's still possible to find some 100. And okay, this one, even I did not take anything particular to this intermediate mass black hole. We have done something else. That is this is about the supermassive black hole, the formation. We know we have a supermassive black hole at the center of the galaxy, right? And usually it's about, we can have like 1 million solar mass, even in a very high ratio, 6 or 7. And so that means the supermassive black hole can form very fast. So how fast it can be? Another question is how could supermassive black hole form so fast? Oh, we don't know what happened in the very early universe. So let's take an example in the local universe. It's usually very difficult to fall into the supermassive black hole because usually when you have gas or star, you always have energy and no momentum. So in order for the material to fall into the supermassive black hole, you need to lose your momentum and the energy, right? And so that's the idea. So similar, how can we do that? In the answer, we got a molecular cloud, which are much mass and coming cloud, and then the star. So it will be similar to the intermediate mass black hole. They can collide with atomic cloud and collide, you can say interaction. That's the main dynamic friction. Interaction with star and atomic cloud, and then you fall into the central very quickly. That's again dynamical friction of molecular cloud. Very similar to what I'm talking about intermediate mass black hole, but this is about the faster formation of the supermassive black hole. But fortunately, I talked about this. I say during the merger, the molecular cloud will fall into the central galaxy. I think some students might still remember I talked about that in galactic astronomy. again, well, actually, I also talk about that in a conference talk in, let me say, in 2009. So I had that idea very, very long time ago. I never really do it. But fortunately, I cooperate with Ken Chen and Lin Qifeng, and so he finally, using that idea, and they can do the simulation. Well, that's good. So, and just get started here. So I don't know if I'm not quite sure it's available published or not, but it's accepted, okay? And you can see that we can form supermax graph very, very clear. This is a dominant and that is the emerging. That's the same idea. And more relevant to the intermediate mass graph is that, well, actually, the in the models, we don't have a central supermass graph, but instead we have some seed, like a 10 to the 4 or 10 to the 6 solar mass. Sometimes graph is a seed around the central region of galaxy. But then you find out that seed of massive black hole would very, very quickly go into the center and then become some of the supermassive black hole. That's how it is built, about 10 to 10 to 6. So that's why I'm talking about it. We've got some intermediate masses. We fall into the center very quickly. This is a
There is the assumption that there is already something in the center, and then the molecular cloud formation would.
They are at the beginning. They actually were doing the simulation very from scratch. Say, so we have some mass, but at the beginning they don't have supermassive black hole, but instead they have some set of massive black hole. So they can put forward and say around the central region, but then this set of black hole very quickly go into the center and become supermassive. So we cannot even display that part without around that. That's why we very quickly, and then after that they also very quickly accumulate a lot. And then later part they can accumulate like merger or something still. And then we can, within a very short time, right? We have been here already reached into 9.
Is it true that if you start with a 100 solar mass, stellar mass, that becomes also grow very, very quick?
At the central region.
Yeah.
I don't know. So we don't, I'm not quite sure. I did not do a simulation. But I think the simulation is about 10 to 4 years. Yeah, but then they can accumulate. That is the idea why you cannot see intermediate mass. Even though we did not address intermediate mass.
But how do they provide the molecular cloud in the first place?
Well, you just assume they are molecular cloud.
Always, right? Always molecular cloud over there, and then it's
Not
just
always. No, you have some molecular cloud outside, at the outer part, even in the outer part. It's not at the central region. But during the simulation, you can see the molecular cloud can fall into the center, but the atomic cloud and star did not fall into the center. And that is the region that is caused by dynamic region. Okay, and
Because of the density?
because of the mass,
Yeah, mass as an entity.
and right, because molecular cloud is a bounded system. Is the time the atomic cloud is not bound, it leaves. And because it's bound, so we can have that. We can have that inside. Okay? Now, let's talk about something very strange. Not very strange. Well, we know the spiral pattern. And we also have a spiral. This is Capricorn. This is a galaxy. This is seashell. We also have a spiral. But what's interesting, the spiral is a very particular type of spiral, like logarithmic spirals. They are logarithmic spirals. All these three have logarithmic spirals. And people probably know why seashell have a logarithmic spiral. They probably know like typhoon, but I don't know because I'm not the people doing the field. So I'm not quite sure how well they know. I know how to create that. So we have a logarithmic scale. Now how can we have logarithmic spiral in galaxy? We always know there's a spiral, right? And we explain the spiral in density way. It's caused by density way. But why the density way have to be logarithmic? Well, first of all, what is logarithm? Logarithmic spiral was an equation, right? R. I mean, the pitch angle, we call the pitch angle is constant. It is this form. The pitch angle, I mean the spiral, and we have a shape of spiral, and we plot a circle past the spiral, then the radial, the circle, the angle between the circle and the spiral is the pitch angle. Okay? So the pitch angle, if we got a logarithmic spiral, then the pitch angle is constant. I mean, no matter R is small or large, then the pitch angle will be constant. Okay, that is the definition of logarithm. And of course, well, spiral arms of spiral galaxies can be approximate. I mean, it's very close, but not all. Okay? Some of them will be very close to the logarithmic spiral, not exactly. Okay, so the question would be, why should a spiral arm of many spiral galaxies is close to logarithmic? Or why should they close to logarithmic? Is that ideal, or do we have any mechanism to clear that? Any idea? Well, of course, I don't know the answer, but that's why I can guess. I can guess. Okay? So, do we have any possible method? The first guess is there any possible mechanism to produce logarithmic spiral in our galaxy? Okay? And to do that, let's see another mechanism that will create a logarithmic spiral. Okay? So if we got when you a hawk and go through this prey, right? Like the hawk try to catch the rabbit. The rabbit will be wrong. Well, this is the first should run in straight way. Otherwise it's too complicated. Now the hawk, we're looking at the rabbit in the fix. His eye and his direction of flight, you keep it in some fixed angle. You keep it in a fixed angle, and then of course you keep it running, and then the hawk keep it approaching to the rabbit, but they have an eye very at a fixed angle. In that way, the path or the trail of the hawk will become the logarithmic spiral. Will be a logarithmic. So the idea, because this is moving thing, so the idea for galaxy to create a logarithmic spiral, and we try to look into a similar thing they might be able to produce, but they also need to be found related to density. Okay, so we know that spiral density is not a definite truth, right? So, what is the possible mechanism? Well, I don't say this is correct. I have some idea why gas. What is the mechanism of galaxy to produce this spiral? We know in what situation we have spiral. If we have a satellite galaxy moving around the host galaxy, then they can create spiral pattern. So that means a satellite galaxy, they can use a spiral in the host galaxy. Then, so let's think about when the satellite galaxy passing through the host galaxy, the relative point L4 and L5 will have fixed pitch angle relative to the center. Okay, so this is I'm using this. People will be more familiar. This is like L4 and L5, right? You relative to their center, right? Here. This angle will be fixed. Okay, that will always because you have relative here, because this is, if it is rotating, right? This is fixed. But how about if this is even closer, their relative center is the same, right? Their center did not change. So in that mechanism, you can see the L4 or L5 relative to the host system or relative to the host galaxy will have been a fixed pitch angle, which means the path of the path or the trail of the L4 and the L5 will become a logarithmic. And it's interesting because we know L4 and L5 is some kind of potential, it's unstable potential, relative potential, so that the material can fall into that potential. A little bit similar to the density, the idea of density. So I think that is one possibility to create a logarithmic spiral in like we have a satellite galaxy and we have host galaxy. And the spiral line looks like, or it is part of up. It should be looks like logarithmic. That's one way to create. I don't say this is definitely the answer. That's the one thing interesting. I mean, so interesting. You might think about why we have logarithmic in galaxy. Why we have logarithmic in galaxy? There's no reason. I don't know. At least we don't know what's the reason for that. And this is just some possible mechanism. I'm thinking about that. They might be able to add logarithmic spiral. Okay.
So if the neighboring, the density of neighbors
Okay.
different, for example, in your even in group of gas, then the spiral pattern will be different. So what you are saying, with this mechanism,
Yeah.
a standalone single galaxy will not develop spiral patterns.
Single galaxy. Yeah. Yeah, okay. I think in order to develop spiral pattern, you need axis symmetry. A symmetric, axis symmetry, potential, right? Then you got a companion galaxy. Satellite galaxy is a way, right? Axis symmetry. Right? Another way is that you got a bar. So I'm thinking about in order to get a spiral, usually you probably have some convenience. Even some convenience are very small. Okay, now let's talk about something deeper. It's mean that's not so many math. Maybe the math is not very complex. Not that interesting. We know there are UFO, right? Everyone like a UFO. Everyone like what is unidentified flying phenomenon. Oh, but it's very discovery. To do research about UFO and UFP. Why? Because it's some kind of trend. Well, they don't repeat happen in the same place, right? That's why you can't do research. You can't do research if you cannot do the experiment again and again, then they call they are transient. Right? So it's difficult. So if some people tell you they are expert of UFO, they must be lying, right? Nobody knows what is UFO, what is UFPs, right? Then now repeat, and it's a transient and a local. Well, but everyone here should know that our institute is doing transient astronomy. We are famous for transient, so we know how to do transient. How to do it? You need to do all sky survey and just keep monitoring in order to do that. So then we think about it's similar, what we can do, or how can we try to do. Then we know that there's if we were some track aspect or cleaning, how do we track that? And now we usually using some network camera, right? There are camera everywhere. In the road, on the road, almost everywhere there are camera. So you always can track down what is the accident, right? Even this accident, traffic accident is also we can try to track. So we have monitoring camera every all the time. So similarly, we can try to, it might be possible, we can try to track UFO and UFP if we got a network, both sky camera. You don't need a very big one, right? Just small camera, but you need everywhere. And so the idea will be, if there are some UFO phenomena happen here, the difficulty usually will go far away and people cannot track it. But if you got the camera everywhere, you can just like you are tracking the local criminal or track the accident, we know where the UFO is going. It's too fast, we cannot follow. But if we have already camera everywhere, we can try to track it. I think it's not possible. This is probably not too expensive, I don't know how expensive, but what I say is this idea. We can do it. But it depends on how much money to spend. It's not unaffordable by our human time, I would say that. Okay? It's not unaffordable. You think about there are so many cameras almost everywhere, right? So it's not very expensive. It's just how big area you want to cover.
They usually go where you have no cameras.
Yeah, well, that's one thing. You need a very, very big network.
Don't tell them where the cameras are.
Yeah, but that is one way. Or maybe that I think it might be just most of them are so.
This one you will do after you pilot.
If I got money. Now that's one way to do it. I don't say we will be able to do it. But what I say is that it's not impossible. The difficult part about UFO is usually we don't know how to do research. It's just transient and happen locally. So let's take it first. The commentary first, before we can do the spectrum. Okay?
If you got so many cameras, you got a lot of data needed to deal with. So you need artificial intelligence to help you to do that.
Maybe not. Why? Because you don't have to keep the data all the way, right? You can, for example, if you have data, then you can speed up. And here we got an alert. We only keep that data. So
But they are unidentified objects, so you don't really know what you skip.
Yeah. You're right. But what I say is we only try to study those have been, well, many people
Abnormal.
observe, right? People know there's a UFO happen, then we can try to track it down. It's like an accident. People know there's an accident happen, then we can try to track in back what is the what happened in the accident. We don't have to tracking everyone moving around the road or something. Okay. Now let's talk about something. Yeah, I think most of the students who have worked as PA in our stereo universe might know this. But it is about the night over the room. This is even the problem I want to answer or try to address here is one other star here. Another star. For those students working with my PA, you know, how do I explain this? This non fit, okay? Because because that is slightly different. You can need the shape here and then the shape of the real. Big difference are very slightly different. And I won't explain here, but why I explain this because of the rotation. And then because the painter is painting from the left to the right. And so when you practice, when you're painting this is their height. When you go here, the earth is more rotate, and that's why this is got a straight up. It's very different from the real thing. Because it's not at the image and then practice. Because the real is really practice on site, and it takes about like 2 hours. So the question is, what is a star? I did not try to answer this in my talk, but it can be done if you try. You need to go back up higher, and I think there are some stars. You can track it down. What is the star? Because in the real image, you cannot see stars, right? Some stars is almost very identified, but it's actually a different position. But all these are due to the rotation of the Earth. That's a very simple way to do. That might be a project for junior high school student, high school student.
That's very good. I like this. So when early you whatever, and then later, and you call them improper motion.
Okay, so that's the idea. You can try to do something very junior high school project for this. That's interesting rotation of Earth. Well, I don't have time. There's something about our very quick. Another question is about dynamics, right? The question is when we should see the dynamic collapse. In the early universe, we have a one-to-one, variant dynamic relation. But what is the transition scale? I'm trying to call it. In the molecular clock, for example, it's 10 to 6. We don't see a dynamic. On Earth, dynamic. So, and Jones galaxy, you say yes, probably will have dynamic. So what happened? How big can we see dynamic? That's a problem. 1 kbc, yes, I think it's related to a scale. 100 pasecond, I'm not quite sure. I'm not quite sure where we can see dynamic. That's some issue that we can start with. Another interesting is the evolution of gas. We now know there are some big gas, right? Some very, very big gas in a very early universe. And at the same time, there's a big supernova, hole, right? And we know there are also some galaxies that are actually formed late from the merging of some gas. So that means some galaxies that are formed very big and early. There are big galaxies formed very early. There are big galaxies that are formed late. So actually, you can imagine the evolution of galaxies. Maybe you can think about the dichotomy. How to pronounce it? Evolution of galaxies. So what I say is that they have 2 different ways. Evolution of galaxies, right? 2 kinds of galaxies. And then because we usually think, what is the origin? Maybe there are 2 kinds of elements. Probably now, we don't know. But if there's a relation between the mass black hole and the gas, now that's what I mean. What is evidence to show that? Then we should see 2 kinds of supermassive black hole. And let us how big. I did before. I think that's we have if you plot a barge and the upstream, you can see there are two distributions. Both the low part and the upper part, they will distribute like a normal distribution. Okay? So that means if we assume there is some relation between the barge and the massive vehicle, and if the velocity of oxygen 3 is related to the mass of the mass vehicle, then we there are two distributions of the mass vehicle. And of course, this is more complicated because the two distributions might close by gas. You might have two different gas. But the even more complicated is machine might have two dichotomy distribution of gas. Then the galaxy of course is different. So they will be different. I have not clear answer, but I think there's some interesting phenomena here that people can try to answer that. Another related is the relative distribution. I think I mentioned this last semester, but let's go to this. One is about the morphology of gas. About the galaxies, we have highest chance finding a similar to in SA and SB. Why? That's because in the universe, there are less gases with type of SA and SB. There are, but let's forget all of them. We just want to answer this. One, if you look at the distribution of galaxies, the white one, there are much less galaxy here. That the picture is 14.5 plus SASB. I mean, we have much less SA and SB relative to other type of gas. So why? Why we have less SA and SB? The answer, of course, people don't know. But my idea is that is because SASB, the formation of SASB is by the minor merger, like our Milky Way. We just keep a merge with some small gas. If we don't have big merger, it will become liquid. It destroy the disk structure. But if you have minor merger, then you still have disk gas. But at the same time, also minor merger will contribute to the barge. And so that means in order to have SA, so you have big barge, you need many minor merger. You need many minor merger to form SA, which means that you more interaction. So that is why you have less. That's my answer. Why we have less is let's be in the universe. So that form minor merger. We have less chance. This is we don't address that particular problem either. This is just to show the minor merger can increase the barge. The barge mass increase. You got minor merger. Increase by minor merger. Yeah, that's a sound, but I know you can try this problem. Right there. Okay, then that will be the end. Sorry. Okay, so now it's time for questions. Anyone has a question? Yep.
The sea in the center and two molecular clouds colliding and maybe forming a possible supermassive black hole. Can we have a minimum gravitational field needed to trigger that production of for the supermassive black hole at the center?
What kind of, I don't understand the question.
He said that 10⁴ solar mass seed will assumed in the center, and then molecular clouds will collide, and
For the initial stage, you will probably from the thick, the fold that pass. can become the seed sugar, become the initial sugar.
So 10.4, can we find a minimum mass or minimum gravitational field, not just by one seed or maybe collection?
I think there are some distribution. Okay, let me see. You can read a paper by Qi Hong. There are some assumptions of the distribution of the seed black holes. There are some assumptions about that. You have some characteristic of density, and there are some formula. And the little formula to see how many black holes. There are some relations. They shall take something relation to do that. What I want to say here is that we don't assume that the region is safe. We just assume something according to the formula. But then the supermassive black hole, the initial supermassive black hole will form that. Okay, any other question? Yes.
I would like to thank Changyan for this talk. I learned a lot. You know, when students graduate from here, they know many of the answers. But when a professor graduates from here, they know all the questions. So very good. I wish every faculty member or a smart person can do this. Just to inspire new problems. Thank you very much.
Okay, so we have many alumni of our institute today. So anyone want to say thank you for Mr. Huang? or anyone want to tell us a good story about you?
Oh, yes, yes.
Him?
Yes.
Oh, yes.
Yes, yes, yes.
Usually they have that story.
We will take that story.
Anyone? Yeah, yes. Not necessary. That's why let me say, okay, usually the big answer early, I think early time. Okay? But the big galaxies from late, they could be really close. Spiral. They can be both. So in other words, you see, they probably there are two types of related, right? One is the formula, the other is the formula. And they might have size difference. Yeah, they do have size.
May I ask which equation do you like most? Related to astronomy. Which one?
From equation. I think I talk about that equation in dark astronomy, in theoretical physics or something. Yeah. Why I like it is because that equation tells us how it's related to the Black-Scholes equation, right? And the Black-Scholes equation tells us how to make money in market. It's a background equation. It's similar. We call it really Black-Scholes equation, and that is it tells us how the evolution of your price of your bonus change. Not bonus option change. It might be slightly difficult for you if you don't invest it in stock market. Okay, OJ, you want to tell us something?
I thought I took your course, but after your talk, I'm not sure.
Yeah, that's good. You have more questions.
Yeah, I would like to take the chance to say thank you to Professor Huang that follow as a master student and PhD student that he inspired me a lot, not only in astronomy but also life. So I think here, but not just Professor Huang and all professor and people here makes me a better person. Thank you.
Next. Okay, go on.
I have a question about the big deeper painting.
Okay.
Yeah.
Which one? This
Yeah.
one.
The painting one goes something wrong because the seven star composed of the big deeper, but the fourth one should be the thinnest one, not the brightest one.
Some of them may be binaries.
Yeah.
They are artists.
Yeah.
So you can see this is a thin one. That's right. You are right.
And the other three, you say some of them, no, on the left, right? You mark, some of them could be below the horizon. And I bet you,
No, I think at the beginning, you see, if when this one is almost vertical, then this three should be below this one, right? Let's say by in the top, you can see these are almost the same size.
He's running out of space.
Okay, actually I have an argument in the course when I teach this very inverse. That is, you might say, well, it could be wrong, right? That's a painting right then, so it could be wrong. But actually, if you plot, you try to measure the distance. The distance, we know this is about 5 degrees, okay? From the astronomy 101, you know, this distance is about, and then you know what is the height here? This is related. It's about 13 or something. You should try something. 13.6 something. Then you go, you know, the 5 times you go to the polar star, and the height of the polar star to here is relative to the latitude, and it's exactly the same as the arc. So that means when we plot the distance between the angles, it's very accurate. And so it won't be possible to make an error at the top.
Maybe the weather condition.
Maybe. But no, the weather condition will make it why you look at brighter than that. That's the weather condition. But they don't change it a lot.
Maybe you
Could be. I don't know. Yeah. Okay. Anything more? Anything?
I think I also would like to thank Professor Huang. I mean, well, I think Professor Huang is the professor that in our institute who doesn't want to push too much to their student. So it reflects the year that we need to graduate. But I think, I think it's very interesting that the professor always give us the direction of the what we possibly will get something through this path, but he just doesn't tell me how to do it, and we just try to do it ourselves on the track, and we finally do get something. So I think it's a very although it takes time, but I think it's a very inspired kind of. I mean, it's a very inspired, or you can inspire kind of the kind of teaching from Professor Huang. Right. So I would like to thank Professor Huang.
Okay, anyone else want to say something? No more? Okay, then let's thank the speakers. Okay, I think we should take a photo using this opportunity. So, yeah, the camera is waiting. So let's move to there and take a photo.
这个不会360度转。
哎呀，没有那么高级，太高级了。我的，你全程你好专业哦。现在是我的职业，是不是？对，我先哈。这在我的频道，在我的频道，在我的频道上，这是直播，在我的频道。对，刚才在我的频道上直播，按赞、订阅、分享，谢谢。等一下帮你分享。会啊，我会存着啊。可是这直播怎么搞进去？
中间太少，再往中间很松，旁边很多人，中间都没有人。好 ，OK， 重新再过来一点。
挡到人家了。
好，看这边哦。来，1、2、3。OK， 好，过来吧。下去，你继续。
专辑，
你躺中间啊。
这 OK 可以。来，1、2、3。OK， 3张，好了，好了。谢谢。
对，我也这样写。
我待会再传给你们。
我们还有。
那你不是要进来？
那不能设定时吗？
请别人帮你拍啦。
对啊，请别人。
我只帮你按快门，那个地方传输设定。我们实验室
有。还没有来，还有没有回来？超过。谢谢，我帮我把这个。是啊，先生打字，我已经长大到大到要死。不要你去，这样就谁嘛？哎，有这样吗？
开心。
1, 2, 3. Another one. More one. Okay. 3.
Count to 10.
Okay, thank you. 哦，你还举手，好。可以，没关系。今天有什么要做的？
老师，你明天那个我们定6点半，你就早点到。
可以啊，我可以到6点多到啊。
好，那个我觉得你时间可以。
那个是下台给
不是直播。
有问题
要访问老师吗？
要访问老师什么？
知道啊。
坐在那里聊个2个小时。
要访问老师什么？我没有想到任何问题。UFO。老师研究多元。
大家说几句话。
真的吗？
老师他
还有远端的，对，
就是有宣儒跟验真，还有正宗。
他说你都把他图放上去了。
回到台湾
他们要说什么？
嗨。
嗨吗？
嗨。
多讲些话。
要多讲些话，要讲什么？
不是啊，你现在是有人要讲话还是？
没有了，没有。老师你要说什么？你也要说什么？
我知道是直播。
我要说什么话？
有老师那
就当做
明天见了。
大家在你面前。
刚才有听吗？
有他们这个，所以燕珍就说图被放上去，他有发现。
对。
而且他说他之后还有人继续做，所以他对。
非常安慰。
对，
非常不错。他可以继续做啊，他现在在干嘛？
燕珍现在在干嘛？
不知道。
上次讲说他
好，这好离职啦，
他又换工作了吧？
对，
叫他可以继续回去做 post
压力好大。直播的时候被给压力。
老师那个我们本来那个蔡兆伟。要不要讲一下？本来蔡兆伟陈正远说有没有直播，然后手上是没有，但我没有想到阿听有，所以你跟蔡兆伟讲几句话好了。
蔡兆伟有在上面，
他现在没在上面，可是我事后会把连接丢给他。
连接会再 share 出去，对。
好，蔡兆伟，你现在虽然没在直播，你之后如果看到哈，你也可以看你要继续做什么研究都没关系。那有空回来台湾，我们再见面，或是去日本，我会去 April。你如果有去的话，我们也可以再聊聊看。
是去 April。
对啊，对，我会去 April。
好，他说他在国外。
OK， 好，没问题。
你说蔡兆伟？
不是
验证吧？
验证做专案助理研究员，对。
验证你其实可以直接回应直播，我其实看得到。
可以的。
好，可以了。好了，那就直播结束喽，大家拜拜。对，怎么样？
你现在用手机拍的是高级型？
不是。
哦，你是直接用？
我只是手机而已。